All right, welcome everyone to the last day of the school. Congrats on getting this far. So the plan for today is that we'll hopefully all of you have at least looked at the exercise, because today we'll make use of results that you derive from the exercise, namely the symmetry in the Ising CFT, and you'll study dynamical consequences of these symmetries, and also what we can do with these symmetries, namely how we can gauge generalized symmetries. Yeah, and then we'll use that example as a testing ground. So first of all, let's summarize. Let's briefly recall this important axiomatic constraint we wrote down last time, namely modular covariance of the symmetry enriched CFT. So what we mean concretely is that suppose you have a symmetry described by a topological defect line, let's call it D. We can study the torus spreading function. This is the torus spreading function with a complex modulus tau. We can study the torus spreading function decorated by this topological defect line in two different ways. One way is to have it oriented in the spatial direction, like this. Okay. Another way is to have it oriented in the temporal direction, like this. Okay. Keeping track of the orientation. On this side, we define the corresponding Pauli function as the upper d as a function of tau. Over here, as a function with lower d. Okay, that denotes the trace over the twisted Hilbert space. So here, this is the trace over the twisted Hilbert space. Here it's a trace over the vanilla Hilbert space that includes the symmetry action. And we learned from the previous lectures that these two configurations are related by a large diffeomorphism, which can be thought of as a combination of the transformation on the tau parameter, set into -1 over tau, combined in general with the Weil transformation. Okay? In the absence of Weil anomaly, this leads to this relation that this torus spreading function with the defect line acting in the spatial directions is equal with the torus spreading function with the defect in the temporal direction up to a change of the modulus parameter. And very explicitly, this leads to the following relation, that the trace over the original Hilbert space, including the defect action, weighted by now familiar evolution parameter coming from, the evolution from time evolution from the Hamiltonian, as well as spatial shift from the translation operator, leads to the following relation. Okay. And the Q tilde is defined as the e to the 2 pi I tau, where tau is set to -1 over tau, and so on for Q tilde bar. Okay, so it's the S2 version of the original Q parameter on the left-hand side. Now the important property of this equation is that on the left-hand side, it carries information of how the topological defect on the original Hilbert space. So it tells us about the charges of operators in the original theory under the symmetry. And those properties are constrained by the right-hand side through the fact that the right-hand side emits a positive integral decomposition into Virasoro blocks. Okay? Because there's no symmetry action, this is literally a trace over this Hilbert space. And because this Hilbert space respects symmetries by both Virasoros, this has positive integral decompositions into Virasoro blocks with degeneracies. Let's call that Nij, where you sum over the representations labeled by I and j, weighted by the corresponding characters. Okay. And this is a very powerful equation, despite how simple it looks, because this is the equation holds for for Q and for arbitrary Q and Q bar, as long as the tau is on the upper half plane. Okay? So it's really a functional equation, and combined with this property that this number has to be in the non-negative integer. Sorry, non-negative integer. That leads to strong constraint, which you explore in the problem set in the case of Ising. In which case, you can postulate, so this has c equal to 1/2, and the conformal weights are restricted to only 3 values. And we know already what are the states in the Hilbert space by solving the modular bootstrap equation as we did in the previous lecture. And then the left-hand side of this equation, okay, you can postulate the most general topological defect acting on the Ising CFT by its eigenvalues acting on each of the 3 operators, the energy, the identity, the energy, and the momentum. Sorry, energy and spin. Sorry. So these are the identity operator, and this is the energy operator, and lastly, we have the spin operator. Okay, so this is the most general ansatz that capture a putative symmetry acting on the Ising CFT, and A1, A2, and A1 over 16 capture the corresponding charges. Okay, and the upshot is that these charges are highly constrained by the right-hand side, because the right-hand side is equal to positive integer combinations. Sorry, the right-hand side is equal to the positive integer combinations of the same characters that show up here, just up to a change of the argument from Q to Q tilde. And you know how these characters related by changing from Q to Q tilde are related by the S transformation. And this together with this equality allow you to solve for the possible values of A. Okay, so first of all, because this equation is linear in the characters, whenever you find a set of solutions to A, if you take positive linear combinations, because you want to preserve on the right-hand side, you have integrality and positivity, you can take positive integral linear combination of a given solution to this set of equation, it will still be an equation. Okay? And what you find from the homework is that there are a set of independent solutions independent over positive integers. And these solutions are given by respectively when all the A's are equal to 1. Okay? This is the trivial solution that you expect coming from having a modular invariant Penning function. And this corresponds to the case where the symmetry does not act at all. It corresponds to the trivial symmetry. And another solution is given by when the symmetry acts almost trivially, except when it acts on the spin operator. Okay, has a minus sign. And lastly, you find the one that we're after, the most interesting symmetry for the purpose of this school, is this Kramers-Wanier duality symmetry, which has the following solution to this coefficient AI. Okay? And this is the famous square root 2 that show up in previous lectures. And this 0 also is a hallmark of the symmetry being non-invertible. So as I said, this will correspond to the trivial symmetry, and this will correspond to the eta symmetry, and this generating the Z2. And this is the duality symmetry. And already from the parametrization, description of this putative symmetry, acting on the operators in the original Hilbert space, okay, which are captured by these eigenvalues. So I should also emphasize that the reason that we can only focus on this, instead of having matrices, the reason that we can focus on just numbers over here, and that's sufficient to completely nail down the symmetry action is because there's no degeneracy in the operator spectrum. For a given conformal multiplet, there is only one operator in the Ising CFT. Otherwise, in general, the symmetry action are not completely nailed down just by the eigenvalues. There will be a matrix. Okay. And with this information, we can deduce some consequences. And so as I already saw, of the symmetry of this symmetry. First of all, we can see that they furnish this set of fusion rule from this description, namely n squares to 1 plus eta, as you have seen in previous, I guess, in Shuhong's talk, and eta squares to 1, as you expect for the Z2 symmetry generator, and the duality defect absorbs this Z2 symmetry defect as follows. Okay. And we also see that when we act by, so using the operator state correspondence, we see that when we act by this duality defect n on the integer operator, okay, just going to this formula, you will find that this is equal to minus square root 2 multiplying the integer operator. And minus square root 2 is precisely minus the quantum dimension of n. Okay. And this is what explains this word identity using this symmetry property. This is what explains the word identity that this gives rise to the word identity that explains the vanishing of the correlation functions of an odd number of integer operator, especially the case of a 3-point function. And this other eigenvalue tells us that the spin operator, when you encircle by the duality defect, give you a 0 operator, namely the map between the spin operator, the map imposed by this duality defect to the spin operator in the untwisted Hilbert space projects to a 0 vector. Okay, but as you'll see later, and something that you can already kind of imagine is that this diagram that corresponds to a map by this duality defect acting on the spin operator to the twisted sector. Okay, this will not be 0, and as we'll argue, this will precisely give you the disorder operator. So I'll be using the convention where the solid line for this discussion. I'll be using the convention where the solid line represents the duality defect, and I use the dotted line to represent the Z2 symmetry defect.
Can you remind me what is the exact argument that the 3-point function epsilon 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 is 0? Because you have to somehow start with n at infinity.
Yeah.
It seems like
yeah. So let me explain that.
Some of the rules we never discussed.
Yeah, so I maybe only mentioned in words, so it's clearly that we need to explain that. So the idea is that so imagine that we're on the sphere like this, okay, and we can nucleate the bubble of this duality defect n at the cost of its quantum dimension, right? And then we can expand. So when we expand, this give rise to these pictures.
But here, you remember, I was asking the question.
Yes,
what are the rules for moving?
That's right. So that's what we're going to come to next. So it's a little bit acausal. I agree with you that when we expand, we have to pay the price of the F symbol. It may ensure that the square root 2 are in the right place. And at the end of the day, it's the sign that matters. Okay. So. So maybe we'll come back to this.
Okay.
Yeah. Okay. All right. And this is also related to how to derive this this property. Okay. All right. So so I will not derive the. So this is. Let me also just say over here that this set of fusion rules captures the part of the information about this general symmetry. But it's not all the information. As we explained last time, a very important information associated with general symmetries are the F symbols. And together, the fusion rules and the F symbols give rise to the fusion category. And you can ask whether there's a solution to the F symbols. Of course, the solution is guaranteed because we have a physical theory that with this symmetry. And the solution to the F symbols I wrote over here. And these are the things that this is one of the few cases where you can actually easily solve the Pentagon equation and find the explicit F symbols. Okay, so the F symbols tells you the change of, as I said, F symbol is nothing but the change of basis associated with fourfold junction vector space. So the idea is that you look at the fourfold junction with some 4 external legs. So you take the radial quantization and take this to be a quantization slice. So this picture specifies a particular fourfold junctions between 4 external duality defects. Now this junction vector can be represented in different ways. It can be represented by a junction vector using this picture or by this picture. And the change of basis between the basis here and the basis given by this picture and this picture is as follows. Okay, and similarly for the last picture. Okay, so you see this important square root 2 that will be important when we make the argument based on the word identity to deduce the word identity. Okay, so if we go back to this picture, something we were just talking about. So we have epsilon here, epsilon over here, and say epsilon over here. And we nucleate the bubble, and we want to expand around like this. Say like this. Okay? And then we can perform the F move over here. Okay? When we perform an F move, there are 2 possibilities. So when we follow the fusion rule over there, so one possibility is, so this is need a little more space. Should have used the other board, but okay. So we are doing the F move over here, so we can either reconnect. Okay. Okay, so this diagram we have up to a cost of 1 over square root 2 using a rotated version of this picture. Okay, and the other diagram we have is with plus 1 over square root 2 with this picture. Okay. Let's see. Right. Okay. So here we use the fact that this operator is odd, so we can shrink this and cancel this square root 2. And here we use the fact that this action gives the 0 operator. This is because in the twisted sector twisted by Z2, there's no operator with this conformal dimensions. Okay, this follows from this bootstrap equation that was written down before. Okay, just in the case of looking this D to be Z2. Okay. And then this, so the end result of doing this manipulation is that you pick up a minus sign for each of these operators. And in the end, if you have an odd number of operators, you pick up an odd number of these minus signs, and from that you can conclude this correlator has to be 0. Okay, because if you contract the circle from the other side, there's no minus sign.
So now you have epsilon surrounded by one circle. Like look at the second term is 0. So let's just forget about that.
That's right. That's right.
Let's look at the first term. Then you have this circle surrounding minus epsilon. So you shrink the circle. You get again epsilon. So then you didn't prove anything.
No. So I was only doing locally. I mean, there's another epsilon over here.
But still, you didn't prove anything. You proved that epsilon equals epsilon.
You close.
No, you need to close. So I'm only telling you the one step. You need to close it 3 steps. You pick out 3 minus signs. But if you close the other way around, so this picture is coming from the original picture, right? You have 3 epsilons and you have a circle. You close over here. There's no sign. Here I'm telling you to close it on one of the operators. You pick out minus sign. And you close it twice. On the other 2 operators, you pick up 2 minus signs. Together you have a total minus sign, and here you have no minus sign. And that leads to a contradiction unless the 3-point function is 0.
It's just that I was thinking that given this picture,
it
seems there is a simpler way to improve it. Just to shrink the circle on the same third operator, and then you get strictly nothing.
No, but that's because you are just exactly undoing what Yifan just did.
Oh, okay.
I mean, each step is consistent, of course. Yeah.
Sure,
Yeah. All right.
Yifan?
Yeah.
And the reason that the second diagram vanished, the one with the eta line was...
Yeah, so that's because, so the eta line, so you're asking about this, right? This is eta, and this is duality, and this is epsilon, right? This is because you can study this bootstrap equation in the case when the defect is just the Z2 twist. And you'll find that in the defect Hilbert space, there's no operator of this scaling dimension. And because this topological operator has to have the same scaling dimension epsilon, it says this operator is equal to 0. Okay?
Okay, can you tell us the twisted sector spectrum?
The twisted sector, I can. So the twisted sector. So this is the small exercise, but for the purpose of this, for the purpose of this calculation, you can find that this the spectrum is is the usual psi and psi tilde. So it has dimension 1, 0. Sorry, this is too small. 1, 0, 0, 1/2, and then the operator of dimension 1, 16, 1, 16. Okay. This you get by starting from the Padding function twisted by the Padding function acted by the eta, which is x0 squared plus chi 1/2 squared minus chi 1/16 squared, and you just do the modular transformation, and you can read off that you have one of these operators in the twisted sector. Only way you have this operator in the twisted sector with unity degeneracy. Okay. And this is also related to the fact that on this picture, this picture will give rise to a non-zero answer because sigma can potentially give you a non-zero answer because the sigma operator has dimension 116, 116. This operation preserves that property, and you do have an operator that has you have to have a candidate operator with that scaling dimension. And you can show the coefficient is non-zero by doing a similar manipulation. So you start with the 2-point function of sigma. Okay. So sigma at point z and sigma at point 0. So again, think about this 2-point function of sphere. Of course, this is not equal to 0. This is just equal to square root 2 times the 2-point function. Sigma z, sigma 0. And obviously, that's not 0. Okay. And if it's normalized correctly, if you normalize correctly, this just gives you the 1 over z to the 1/8. 1/4. Okay. But on the other hand, you can perform F move in this region. Okay. And what you find is that this is equal to 1 over square root 2 times this kind of dumbbell plus this trivial configuration. Okay, I'm just using this F symbol over here. And this diagram, we can again conclude 0, as we already said over here. Okay, so you just left with this diagram. And we know this is going to be something proportional to mu. This operator is proportional to mu. And the fact that the equality over here, so this is really equality, this side of the equation says it's non-zero, says that this coefficient has to be non-zero. And you can normalize it, and you find the normalization to be square root 2. Okay? As you would expect, because this duality defect has quantum dimension square root 2. Okay, is that clear? All right. So with that, we can also write down this set of topological moves of topological defect passing across operators, which is something you also see in previous lectures, presumably also already in last week's lectures. So this is the slightly different but related topological move that you can deduce from the F symbols and together with how symmetry act on local operators. For example, if you have the energy operator and you have the duality defect, when you move the duality defect across the energy operator, you'll pick up minus sign. Okay, this is because when you pass it through it, at one stage it will be something like this, and then you again perform the F move in this part of the diagram in the same way that we described, and you obtain this answer using how the symmetry acts on the energy operator. Okay. And if you perform a similar analysis in the case when you have a spin operator and you try to drag a duality defect across the spin operator, by a similar analysis and using this information, you will find that when you drag the spin operator across, when you drag the duality defect across the spin operator, you will find a disorder operator. Okay, and because in this case that there's no additional circle that I'm contracting, there's no additional factor of square root of 2. Or said differently, the square root of 2 that you obtain from the circle action gets cancelled from this 1 over square root of 2 that appear in the F symbol when you try to accomplish the right-hand side from the left-hand side by fusion. Okay. All right. So this is again a hallmark. This property is again a hallmark of a non-invertible symmetry, especially this property, in the sense that when you pass the symmetry defect across a local operator, a non-local, well, slightly non-local operator that's attached to a symmetry defect tags along. Okay. All right, and in the homework, you will study, well, in one of the homework questions, you study one of the other consequences of having this symmetry defect. Namely, this symmetry defect implies that the CFT is self-dual under Z2 orbifold. Okay, this is the general statement whenever you have the symmetry defect and that satisfy this set of fusion rule, you can show that the CFT is always self-dual under Z2 gauging, which is something we'll describe next in the more general setup. But in the homework, you show this explicitly in the case of icing, okay, which does have this symmetry. All right, so that's about the discussion of this small explicit example of a non-invertible symmetry in the context of icing CFT and the data that specify how the symmetry acts on the CFT. Let's now talk about dynamical consequences. Okay. So we'll first be slightly more general, and then we'll come back to the icing symmetry to make a specific prediction. Okay, so the problem we want to ask is if we have a symmetry, if the given quantum field theory has some symmetry described by potentially non-invertible topological defect lines, and we consider renormalization group flows that start from the given symmetric theory by turning on a local operator that preserves the symmetry. Okay. What does it mean for this operator? So this is a local operator with dimension h and h bar, h equal to h bar, such that delta is smaller or equal to 2, so for it to trigger a non-trivial RG flow. And if this operator preserves the symmetry, meaning that if it commutes, we can tag, you can drag the topological defect across the operator. So let's call it topological defect D. Okay. That's D symmetric. D symmetry. You can drag the topological defect D across the operator O with no cost. That's what do we mean when they say the symmetry commutes with the deformation. Then the symmetry will survive along the entire RG flow. And we want to ask what we can say about the IR phase of the theory. Okay. And there's a very simple theorem that you can prove. And and you probably have seen before, but let me say it again. The simple theorem is that if the quantum dimension of this corresponding symmetry defect is not a positive integer, okay? So as we explained before, from unitarity, the quantum dimension is always bounded below by 1, but it could be some general number. In the case when the quantum dimension is not a positive integer, you can prove the simple theorem that says that the IR phase of this RG flow cannot be trivially gapped meaning the IR phase cannot have a single, cannot just be a single gapped ground state. Okay, it could be either a gapless phase described by a CFT or symmetry breaking, spontaneous symmetry breaking. So how do you prove that? The proof is really just one line. It would be enough space down here. So suppose we proceed by contradiction. Suppose under the RG, the symmetric theory that respects the symmetry D does flow to a gapped phase with a unique ground state. We can deduce the following constraint from the modular covariance property that we drew on the top, which applies to any CFT, especially for a gapped topological theory. Any CFT. Otherwise, there will be further relations.
Why does it have to be CFT? It seems like for any quantum field theory, this should be true.
It's not literal equality, I'm saying, because in relating these two pictures, doing S transform, there's a Wall transformation involved. Yeah. Okay. So I'm using the fact that I mean the CFT and with no Wall anomaly, which is something we can do on the flat torus. Okay. All right. So what does this equation mean? This equation is very non-trivial, as we saw in the case of a continuum non-gap theory. But it's very simple in the case of a gap theory. When you have a single, if the theory has a single vacuum, the left-hand side is just equal to the quantum dimension of the defect itself. Yet the right-hand side is the dimension. Well, it's the trace over the Hilbert space twisted by the defect D by 1, okay? Because there's a trivial Hamiltonian. And the equality between these two equations says that D has to be a non-negative, or has to be a positive integer, okay? And that's a contradiction to this condition. Okay? So we have proved the statement. Okay? So indeed, the IR phase cannot be trivially gapped. But there's much more you can say.
Sorry, what's the argument that D cannot, the quantum dimension cannot renormalize?
Very good. Very good. Very good. So this I did not say. So very good. So the pentagon, so there are many ways to explain that, but let me give you one way. So the pentagon equation that I wrote is a polynomial equation on the F symbols. Okay, and it has discrete set of solutions. And the quantum dimension are entirely determined by a particular F symbol, namely this kind of F symbol where you have identity, you have the identical topological defects from all external legs. Okay, and for that reason, because there's a discrete set of solution, they cannot change under continuous deformation.
Question is related to the question. Since you only need this rotation in the Euclidean space to have this result, you may not need to use the full conformal symmetry.
Sure. But the structure in the original theory requires having the full. I mean, yeah, that's right. If you are only talking about just in the TQFT, yeah.
Question?
Okay. Yes.
Can you explain where the left-hand side equality comes from?
The left-hand side? It's coming from the assumption. So we're proceeding by contradiction. We assume the IR is trivially gapped, and we want to show that the quantum dimension has to be integer, so violating this condition. So we're assuming there's a unique ground state, in which case the right-hand side it just keeps telling us the action of the symmetry acting on states in Hilbert space. And because the Hilbert space just has a vacuum, that just gives rise to quantum dimension.
Is that obvious? That's
So as we discussed before, the quantum dimension is defined by the value of the symmetry acting on the ground state.
You can just comment on if you have symmetry breaking. So if you have two vacuums,
Yeah.
how does it get around?
Sorry?
How does this work? And then there's no contradiction if you have two vacuums.
So very good. So this statement can be refined. This can be refined. So if it's gapped, this statement can be further refined to put constraints on vacuum degeneracy. So in general, having two vacuum is not enough. You need to have multiple vacuum. Yeah. And the precise degeneracy is constrained by the property of the symmetry.
But is it still true that, suppose we have n vacua?
Yes.
Is it still true that this d going to act on each of the vacua just as a factor of the quantum dimension?
So good. So this is why. So in this statement, the axiom that I said so far is obeyed. Okay. So in proving the statement, I will assume there is a unique ground state. Okay. So everything follows. When you have multiple ground state, the everything I said is almost correct up to this condition that it's no longer true that the topological defect acting on the ground state always just give you the quantum dimension because there are multiple ground states. Yeah.
Again, I think this may be a good example to come back to the question how the D is normalized.
Yeah.
You know, in the left graph, D is an operator. You can scale that by any number. It's still an operator.
Yeah.
But somehow we'll do rotation of the right graph.
Yeah.
This scaling D by a number seems as forbidden for some reason. Yeah.
Because of the requirement for this picture to make sense when you quantize on this spatial slice. Yes. So this again, locality for me is the ability to put my theory on the general Riemann surface in 2 dimensions, and then be able to cut and glue and give consistent answer for this given Euclidean observable.
I see. So that's fixed. You can normalize the arbitrary.
That's right. There's a subtlety that I've put under the rug. That is that, as I always said, that I'm assuming there's no Wall anomaly, and if you're on the curved background, if the geometry is not like a flat torus but a curved background, the various diagrams I draw should be interpreted up to the Wall anomaly. Yeah. So in the paper we do comment on that. Yeah.
the right-hand side sometimes can be 0 if you have multiple vectors. Is that right?
The right-hand side? Yeah, the right-hand side can be 0. Yeah, that's right. Yeah. So what can happen is that, for example, just in the case of Z2 symmetry, right? So on this side, if you have symmetry breaking, you could have vacuum which are Z2 odd and Z2 even, and then on the left-hand side we get 0, and that would imply on the right-hand side there's this topological line just cannot end. The trace is 0. Okay, so that would be one example. So maybe that answers Julio's question in the case when D is equal to 1, the quantum dimension D is equal to 1, right? You have to have 2 ground states. For example, the symmetry is anomalous. I mean, you can have a unique ground state, but you can have 2 ground states which is consistent with anomaly, in which case they are charged even and odd. On the right-hand side, it just says the defect cannot end topologically. Okay, is this clear? All right. So let me just mention 2 examples of applying this dynamical constraint coming from the symmetry. Example number 1. So this is I only mention it. I will not explain the details. Detail you can find in the paper. So you can start with the tricular model. So I'm working in the continuum. On the lattice, there are more possibilities, but in the continuum, for the Ising CFT, there is no relevant operator that preserve or that commute with the duality defect. Okay, with the non-trivial defect which have this property, okay, namely the duality defect. But in the tricular model, the tricular Ising CFT more precisely, the C equal to 7/10 CFT. There is an operator. Which is the second energy operator, which does commute with this operator of dimension, holomorphic dimension 3/5 and anti-holomorphic dimension 3/5 that commute with the Ising symmetry. So I should first say that this CFT has a symmetry which is quite interesting. It has the symmetry that's described by the Ising fusion category. So the same Ising fusion category that we saw in the Ising CFT. But there's a tensor product, or more precisely a D-line product, with another symmetry. So it's a composition of the symmetry from described by the Ising category and the symmetry described by the Fibonacci category. And the Ising is what we described already. It's generated by the trivial symmetry, the Z2 symmetry, and the duality symmetry. And eta is the familiar Z2 spin symmetry for the tricular Ising model. And the Fibonacci symmetry, on the other hand, is generated by one non-trivial topological defect W. And it has the fusion rule that W squared is equal to 1 plus W. Okay? And the quantum dimension of W, as you can derive by solving this polynomial equation, is square root of 5 plus 1 over 2. Okay? So this is the famous Fibonacci symmetry. There are operators in the tricular Ising model that preserves either Ising or Fibonacci symmetry under a relevant RG flow.
Okay, but this tensor product just direct tensor, no twist.
There's no twist.
Just direct.
That's right. But it's a tensor product for the category, so more precisely defined by the D-link product. Okay. And under this, so there's this particular operator. So this is just the side remark about symmetry. There's the particular operator that commutes with the Ising duality defect. And you can ask, if you deform RG, if you start the RG by turning on this operator, where do you end? Okay. So there are two possibilities depending on the sign. So let's call that lambda. The two possibilities are either, so because of the argument we just made, it cannot be trivially gapped. So there are two possibilities. Either it's gapless or it's gapped. And you can use this refined argument, which then I did not have time to explain. You can show that it has to have 3 degenerate vacuum at the minimum. Okay. More precisely, you will find that the vacuum degeneracy will be a multiple of 3. Okay, and 3 is the minimum possibility, and this indeed agrees with the result from integrability. The reason being that this deformation actually generates an integrable RG flow. Okay, so this confirms the dynamical prediction that we deduced from the symmetry. And in the gapless case, you will have to end up with a CFT that has the same symmetry. Okay, and the only other CFT with the symmetry, with a C smaller than 1 and with the symmetry, has to be the Ising CFT. So the direct prediction from the symmetry configuration, consideration already tells us that if it's gapless, in this case, has to be the Ising CFT. And again, this is confirmed by the integral RG flow with the other sign of this lambda deformation. Question? Yes?
I have always the question, but is it automatic that if the deformation preserves the non-invertible operator, automatically will preserve the whole Ising category?
Yeah, so that's coming from the consistency of this property. You can derive that when this is preserved, because d squared squares to the 1 and the 1 is always preserved, you can deduce that the Z2 is also preserved.
Yeah. Okay. Question, yes.
This deformation breaks Fibonacci.
Come again?
This deformation breaks the Fibonacci symmetry.
This deformation breaks the Fibonacci symmetry. But there's another deformation, I believe, is the second spin operator. So this tricular Ising model has 6 primary operators, has 3 energy operators, 2 spin operators. And one of the spin operator preserves the Fibonacci symmetry but breaks the Ising symmetry. And you can, again, deduce similar dynamical consequences.
Sorry.
Yeah.
I don't understand how the reverse of the RG flow works. Because, I mean...
The reverse?
Yeah. How do you go from Ising to tricular Ising? If the Ising does not have an operator that commutes with n, how can you?
No, it has irrelevant operators. So indeed, that's a very good question. This is a relevant operator in the tricular Ising model that preserved Ising symmetry. When you turn it down and flow to Ising, you can ask what operator in the Ising CFT that tracks the flow into the Ising CFT, and that turns out to be the TT bar operator. And because it's built out of a stress tensor, it automatically commutes with any symmetry, including the duality symmetry. Okay. All right. So another example that was already mentioned, but let me mention it again. It's a rather interesting example. It's from a paper from Zohar and Kantaro and Sahan et al., where they show that 1 + 1 dimensional, again using general symmetries, they show that 1 + 1 dimensional SUN adjoint QCD with a single Majorana in the massless case, okay, flow to a gapped phase with a huge vacuum degeneracy of the order 2 to the n ground state. There's a small shift of n in the exponent, so that's why I put a squiggly sign over here. Okay, and this vacuum degeneracy is explained by a huge set of non-invertible symmetries in this theory. The set of non-invertible lines is also of the same order, maybe with a factor of 2 in the exponent, I think. Yeah. Okay. So that's about the analytical consequence of symmetry. Let's now switch gear and talk about what we can do with these symmetries. Namely, want to talk about generalized gauging. Okay. Yeah.
Is there like a one-line way to see where the non-invertible symmetries come in the QCD?
So if you cheat a little bit and you think about if you assume that turning on the gauge coupling is essentially just doing the coset, then okay. Let me bring this combination board is a little tricky. Yeah. So there's a proposal of the gap phase. So if you just look at the adjoint fermions, that's described by a CFT. That's the Weissman-Witten model, spin n squared minus 1, level 1. Okay, and if you think that gauging SUN is just amounts to doing a coset, okay, then you will conclude that the corresponding TQFT described IR will be this. Okay. And then the topological defects are just described by the topological defects of this Weissman-Witten model under the coset construction.
So in this case, the coset makes C equals 0.
Makes C equals 0, but there's still tons of topological defects that just coming from the Valinde lines over here, and then there's additional ones generated by the coset. Okay. All right. No, this is not the. I was looking for the hook. Ah, okay. Thank you. There's another hook inside. All right. Okay. Very good. So now we come to the last topic, namely generalized gauging. Okay, and I should say that there's a nice set of papers, very extensive discussion of these topics by folks Runkel and Schweigert. I think starting from this one, and there's a sequence of papers on the subject. They mostly focus on the generalized gauging in the case of rational CFTs, but many of the technology can be easily generalized to the case of general gauging in two-dimensional QFTs without relying on the three-dimensional description. And some of the details was fleshed out in a later paper we wrote with my students, Sasha, who's in the audience. There are many developments. So you can find in this paper the references. I will not be exhaustive references in this lecture because of the time. Sasha and Quentin, who was in the audience, that appeared last year. Okay. And I'm happy to give you more references if you want. All right, so the question we want to ask here is if we give a two-dimensional QFT with a set of symmetry lines, we want to ask what set of symmetry lines, what subset of the symmetry lines can be gauged. And once we decide on a subset, we also want to ask what are the choices. So even if we fix the subset of topological lines we want to gauge, are there different choices? So as we know in the case of invertible gauging, the different choices amount to discrete torsion. So we imagine that there will be a generalization in the case of gauging non-invertible symmetries as well. So a brief flashback to gauging invertible symmetries. Let's look at the specific case of gauging Z2 symmetry of, say, a quantum field theory that I denote by T. Okay. I use this to illustrate the orbifold procedure that you probably learned from string theory class or maybe a CFT class. In this case, there are two. So I put Z2 just to be concrete, but you can do this for any group G. And it amounts to two steps. So it's known as also as orbifold. It amounts to doing two steps. The first step is to do a projection to Z2 even sector. And another step is to, so I shouldn't say the first step or second step. You need to do them in combination. The second step is to include Z2 twisted sectors. Sorry, I still use that word just because the way I write it. Okay. And at the level of the torus Prandtl function, so suppose you want to study the torus Prandtl function, this amounts to taking linear combinations of the Prandtl functions of the original theory. So this is the Prandtl function of the original theory, decorated by this Z2 topological defect in different orientations. So this is decoration. So now I'm just talking about the discrete symmetry. So I'll use the solid line to represent the symmetry defect eta, that generally is a Z2 symmetry. And then there's a twisted sector as well. So this is in the twisted sector. And then lastly, there's this block that's necessary to impose projection. Also, this combination of two is necessary to impose projection also in the twisted sector. Okay. And the reason that this blocks has to come with the same coefficient and this 1/2 is because of the following. I mean, we want to define a procedure, namely gauging or orbifold, which is a map between consistent QFTs to consistent QFTs. And consistency, from the purpose of these lectures, boils down to locality, unitarity, and compactness, and also having a unique ground state. And the locality at the level of the torus Prandtl function boils down to modular invariance in particular, and this relative coefficient are fixed by modular invariance. Okay, in particular, these are related by the T transformation, S transformation, and this is related by the T transformation. Okay. And furthermore, the fact that you want to have a unique ground state leads to this factor of 1/2. Okay. And if you may be a little bit worried about the last graph, because although it seems to be S invariant, you may worry that because this junction in general is defined up to a phase, you could worry that under S transformation, this junction could pick up a phase. And that's related to the notion of anomaly. So let me sketch it over here. So if you look at this junction more closely, you can resolve it in two different ways. Into more fundamental threefold junctions. And in the case of Z2, the threefold junctions are just essentially the twofold junction between the Z2 lines. And the two resolutions can be drawn like this. So I emphasize, again, this junction that parameterize the state leaving in this circle and in this circle and in this circle, because there's a unique junction when you fix the four external legs in the group theory in the group symmetry case. all these junctions are just related by a phase if you normalize them, or in general by a complex number. Okay? But in general, they may differ by some number. And the question you want to ask is there a choice of a definition of this junction? In other words, a linear combination of these guys, such that this property is preserved. And also, you don't want this part to be 0. Otherwise, all these things just collapse, and you have just the original boundary function. Okay? And what you find is that these two are related in general. So this is what I just said. If you normalize things, in general, they're related by a phase. And these two diagrams are also related by a S transformation. Okay? And because S squared amounts to doing nothing, this says this omega squared has to be equal to 1. And that implies that omega is equal to either +1 or -1. Okay? When omega is equal to +1, this case is gaugeable in the sense that we can use either definition. And because it's manifestly S invariant, we have no problem with locality. Okay? So this is also known as anomaly free. But when omega is equal to -1, we have a problem. Because no matter which choice we pick, it's not going to be S invariant. It will pick up a phase under S transformation. Of course, you could take the linear combination of these two, but then it just becomes 0. Okay? Of course, 0 is S invariant. Okay? But that's not what we want. And this case is anomalous, and it's not gaugeable.
But what do you mean that that's not what we want? What we want, like?
Because sorry? Because that amounts to gauging nothing. Because these things are related to one another. If this block is to be 0, this will be 0. And this will be 0. Okay? That's not possible. Okay? See? Because all these three things are tied together. If this will be to 0, which is if you want to be modular invariant, so take a linear combination of these two things when omega is equal to 1, it will imply this is 0 and that is 0. And this is not possible to be 0. Because there's an identity operator where eta cannot annihilate. Okay?
Yeah. When omega equal to -1, if you feel this eta line, the word line, then it's a word line of Fermion or word line of Samian. I think there's maybe related statistics.
Oh yeah. So you have in mind from the 1 plus 1 from one higher dimensional perspective, this will descend from the bulk from a Samian.
From Samian.
Yeah.
That's omega -1.
Yeah. That's the width anomaly, yes. So to give you an example, so this is example of this is already in the Ising, okay? So in the Ising Z2 will have this property. This is something you can check by calculating this particular block in the decorated torus spreading function. You can check this property, namely under S transformation, the phase is 1, okay? And as an example for this, as Xiaogang asked, is the SU2 level 1, which means the Witten CFT, where you take the Z2 symmetry to be the Z2 center. Okay? And this descends from the Samian when you think about it in the TQFT language. Okay? All right. So what is the story that generalizes so this answers when a Z2 symmetry is gaugeable, and you can easily generalize that to the case where the symmetry is described by a non-abelian discrete group.
I'm still a bit confused. Like you said that the fourth term is strictly speaking gray. It's not well defined. You have to see what you.
Yeah.
But you want to define it so that it's a T transformation of the previous term.
As well as S invariant.
So then what we could do is that, first we could just define it, so the third term is well defined.
Yeah.
Then we apply T transformation, we get the fourth term, and then we just check if it's S invariant or not.
Yeah.
It's equivalent to what, okay.
Yeah, but in general, you do not have that information. So to do that, you have to have information about the CFT explicit already.
How do you compute that diagram? So you get, okay, we have these two diagrams.
Very good.
It seems to be the only way to compute.
Very good. So the diagram is a consequence of this local move. So as I said, this W. So maybe I should emphasize this W is an example of a F symbol. Okay, it corresponds to looking at these two different. So I drew it in opposite direction. So let me be consistent, although it doesn't matter. So you're looking at the fourfold junction between the, in this case, just a Z2 symmetry generator. So you'll be doing quantization on this circle, and there's a one-dimensional vector space. There are two different ways to represent this basis in this one-dimensional vector space, this picture and that picture. And they could differ in general by a number. And this number could be either plus or minus 1. When it's equal to minus 1, this is the picture. And now you're asking, how can we deduce this number, this minus 1, in the given theory? You can do that by calculating any observable that contains this local configuration. So for example, you can compute the 4-point function of some operator in the twisted sector, like this. So this could be, in the Ising, could be the psi operator. Okay? And you study the 4-point function under a crossing move, and you can detect this minus sign. Yeah. And you could also study the torus Sperling function. Yeah. But the point is that this is a local manipulation. Yeah. Mm-hmm. All right. OK. So there's a very suggestive way so I'm taking a slight shortcut to describe generalized gauging. But there's a very suggestive way to promote the overflow that we described to the case of gauging non-invertible symmetries. It comes from realizing, well, taking seriously this notion of gauging is imposing projection. Okay? But we see that to be consistent with locality, already at level of the torus, we need to impose projection not just in space, not just in the spatial direction, but also in time direction. Okay? And the projection in the spatial direction implements the first ingredient of the gauging, and projection in the temporal direction imposes the second ingredient in the gauging. Okay? So we propose that when we gauge a general symmetry, so this is a general symmetry defect, okay, which I emphasize would not be simple in general. In the case that we describe above, is taken to be the direct sum of the trivial defect and eta, okay, is equal to, so we think about A as a projection. This is up to a normalization. This will be implementing projection as what it does by this combination. And we think about this combination above as, so maybe I use a color, as inserting this A topological defect with a particular topological junction. Okay? This you can easily reverse engineer based on that picture. So once you have specified A is this topological defect, as we said before, the valid manipulation for topological defect is direct sum. So you cannot take 1 over square root 2 over here, for example. But this is a valid configuration. But this 1 over 2 factors can be absorbed into normalization of this topological junction, which is a point operator. And you're allowed to renormalize your point operators, because that's a local modification for the point. And more generally, for the purpose of later discussion, it's useful to resolve this fourfold junction into more generic junctions. And you don't lose information this way. Where the red line denotes the same topological defect. Again, it's in generally not simple. And now the junctions. So if you want to be careful, I should keep track of the orientation as well. And these junctions give rise to these junctions, depending on orientation, are labeled either separated by M and M dagger. Okay? The reason I want M and call them M and M dagger is because in the preferred gauge associated with the junction vector spaces, and M and dagger are literally related by Hermitian conjugation, and that's necessary to ensure this observable when tau is equal to I is positive. Okay, by reflection positivity.
Sorry, the thing in the middle, the arrow in the middle, is it still A?
Yeah, so every red line is A.
Why is it still A? When you resolve the function, there could be something else.
Yeah, in general, yes. But you want to insist on this condition because you want this to be a consistent projection. So you want to be able to, eventually you want to be able to, so as in the case of the invertible symmetry, you want to be able to freely move this network that imposes the projection without changing anything.
Okay.
Yeah. Okay. So you want to be able to project out any operator no matter where it's inserted. Okay.
So why do you only have the false diagram?
So this is the, maybe I'll put it in red. Yeah. Okay. So as you can, so maybe this is not, if it's not totally obvious, let me say it again. So the A is a projector. So the way you interpret this diagram is that you need to consider the direct sum. So A is distributes into either inserting 1 or eta. So there are 4 possibilities already from this diagram. And the choice of this junction specifies the coefficient of each blocks. Okay?
So basically the fact that only A appears in the middle is just follows from the fact that A is a projector. A squared is A.
Yeah.
Okay.
Yeah. That's right. So that's a consistent.
Sure. Isn't 2A?
Sorry?
Isn't there like some combinatoric factor? Because a projector would be 1.
Yeah. Very good. So but that's related to the normalization of the junction. Yeah. So A squared is isomorphic to A. But then you can pick the normalization such that, yeah, okay. All right, so this is what I just said. So the data of generalized gauging. So I'm just making a statement that the data for generalized gauging amounts to specifying this composite topological object A. Let me again use A to emphasize. And then this multiplication maps, or this is known as multiplication maps, or known as morphisms, or also threefold junctions between this topological defect A with different orientations. And there are also these unit morphisms U and U dagger, which I will explain shortly. And the multiplication maps allow us to specify a junction with this orientation of this external A legs in the following way. And similarly, for the other orientation, now you have A dagger. M dagger. Okay. And this unimorphisms tells us how A can end topologically. So this U specifies how A can end. So a semi-infinite A can end topologically. So you think in my convention, this is the orientation. And similarly for U dagger. Okay, and emphasize if it's confusing, compared to what I said before in the last lecture. I said that we require the symmetry to be faithful, and that implies that a topological defect, if it's non-trivial, cannot end topologically. In that statement, I have implicitly used that a topological defect is simple. Okay. So in this case, when the topological defect is not simple, for example, has 1 plus eta or some other more complicated topological defect, even though it's not the same as identity, can still end topologically because there's an identity channel. Okay. Hopefully that's good.
So in this decomposition, you assume the middle line is also A.
Yeah, all the red lines are A.
I see.
Yeah.
But why usually when you do this resolvation, the middle line can be arbitrary in general. So here there's a restriction. This one.
Well, this is what I said before. So this, first of all, this is the allowed operation because A appears in the fusion of A and A. Okay. And furthermore, this is consistent because you want this line to impose projection in this direction, no matter where the location is.
Okay. Why don't you write the equation A squared is proportional to A, and then it's clear?
Yes, but the point is the following: there are topological junctions with other defects that can appear.
No, but because A squared is proportional to A, then you're guaranteed that you can always rewrite this junction in this form, isn't it?
For the invertible case, yes. But for a non-invertible case, that's no longer, yeah.
Okay, that's right.
Oh, I see. So A squared can be other things, but then you want to, this M is a projection back to A.
Yeah.
M have this,
that's right. Okay. So once again, in the invertible case, because of the uniqueness of these junctions, you will automatically just have A. But in the non-invertible case, this junction is not unique. If you just focus on
choice M, you can have different projection.
That's right. That's what M is doing. Yes.
Okay. But then I'm still confused. Do you impose the condition that A squared has to be proportional to A?
No.
It's not imposed.
No.
Okay.
A appears in A squared.
A appears.
Yeah. A squared is proportional to A in the invertible case. Yeah. Okay.
But only in that case.
Yeah. So let me in case there's a confusion. This is really just an example, but now we're talking about the general story.
Only in this case, the non-invertible line can be gauged. Otherwise, it cannot be gauged. Like
Yeah.
icing.
Yeah. You need this junction to exist.
Okay.
Yeah.
Ethan,
Yeah.
in the picture there,
Yeah.
should the horizontal line be going left to right in orientation? Just for consistency with how you define your junctions?
Did I switch? Yeah, right. Sorry. In that definition. Good. Okay. So I think I may have changed the convention and prepared the notes. Yeah. Okay.
So do you need to worry about that when defining the partition function? Do you need to specify in which direction the A is going? Because A and A dagger don't seem to be isomorphic.
In general.
So then there are different gaugings depending on the orientation you pick?
Well, that information, I mean, it depends on, how should I say? I mean, if the theory is parity invariant, the orientation doesn't matter.
Okay.
But in general, it may, yeah. But I'm only talking about parity invariant theories.
But also the A itself has to be invariant.
Yeah, so in all the cases I know, yes, A is self-dual. It's isomorphic to its orientation reversal. Yeah.
Sorry, I'm a little bit confused because you said something about invertible case versus non-invertible case. Are you assuming which one?
I'm not assuming. So here, we're talking about general symmetry. So we're talking about general symmetry category. Okay, we're no longer assuming. So there is an example, and as I said, I was taking a shortcut to generalize the case where the symmetry is in general non-invertible. We have a set of TDLs, and we take a particular TDL, I call it A, and we ask whether A can be gauged. Okay, and for that to work, we need such a topological junction, and that amounts to this kind of topological junction. So if the topological junction exists, we potentially have a way to gauge. But I have not written down the full axioms yet.
Okay, but eta is not necessarily a Z2 line, or?
No. So this is the example where we talked about above. In that case, it corresponds to a special case where A is literally 1 plus eta, where eta is the Z2 generator. Okay. Yeah, where, as we'll see, all the axioms will be satisfied.
Okay, one last question.
Yeah.
Should I think of these junctions in the invertible case as basically the dual to the choice of discrete torsion phases or something like that?
Yeah, so very good. So in the invertible case, these junctions specify the discrete torsion. Yeah. So as we'll see in the non-invertible case, the different solutions. So this captures discrete torsion. So I put a quotation mark because this notion is for the group case, but the generalization of this to the case of non-invertible symmetry, and this corresponds to the SPT phases that Shuheng talked about for non-invertible symmetries. Okay, 1 plus 1D SPT phases. Good. All right. So how much time do I have?
17 minutes.
17 minutes. Okay. So let me instead of writing down all the axioms, let me just kind of describe a few of the axioms. One basic axioms is that so maybe first let me say that abstract gauging, abstractly gauging with this information, the A and the junctions, amounts to decorations of observables in the theory before gauging by a network formed by A and joined together by these junctions. Okay, keeping track of the orientations. And you want this network to be a mesh of A that's fine enough. In the sense that the A has to straddle all the non-contractible cycles of your Riemann surface on which the observable is defined. And furthermore, if you have local operators in this observable, the A has to also end on those local operators. That takes into account the fact that you want to include twisted sector operators as well in this gauging process. So just to give you an example, if you are looking at the torus, if you're just looking at a torus Spartan function, the diagram we draw above is already fine enough, in the sense that if you insert any other topological, if you insert any other topological line A, for example here, okay, using the consistency condition that I have not written down yet, you can reduce this back to this above diagram. Okay, and if you look at the 2-point function, so if you look at 2-point function of operators, then a fine enough declaration by this topological network generated by A and the junctions M will be of the following type. Okay. Again, I'm dropping the arrows just to save time. And with this junction, once you draw the arrows, this junction are specified M and M dagger accordingly. And this diagram, in the theory before gauging, taking into account the topological defects, computes the 2-point function in the gauge theory. Okay. So this is a general. Abstractly, this is what they do. The gauging is a process to produce observables in the gauge theory, starting from the ungauged theory by taking into account the network of this object A and the morphisms M. Okay? And these are the examples. Okay? And the consistency conditions is a version of imposing gauge invariance for this background gauge field, here represented by the network of A. And that amounts to saying that this kind of declarations should be independent. As long as they are fine enough, they should be independent of further triangulations, like further triangulation and inserting more topological defects A. And
can you show that there are only finitely many choices?
Sorry?
Can you show that there are only finitely many choices of abstract gauging up to some equation?
Yeah, so that's coming from the consistency conditions. So the consistency conditions, so this is from consistent gauging, consistent conditions on gauging. It's coming from requiring, in particular, the following consistent conditions. For example, this kind of topological moves that you saw before. So again, will be equal. It will not play. It will not. There will be no cost to implement this topological move. So let me just drop the arrows, because this diagram will be true for any assignment of arrows. So consistent gauging in particular requires this condition. Namely, these two are just related by a topological change in the network. And by consistency, namely the generalization of the gauge invariance to this non-invertible case, this topological network should give rise to the same observable, gauged observable. And this is one of the conditions. And by choosing the orientations, it leads to this set of conditions that defines the symmetric special Frobenius algebra object A. Okay, so all these words in the front specifies consistent conditions on A, such that what I said is true. Namely, the gauging produce observables which expects locality constraints. Okay, so here I'm only writing down the ones that correspond to the Frobenius condition.
This is like a normally free condition?
So at the level, if you compare to the case of the group theory, where the symmetry generated by the group, this is a normally free condition. Yeah. So the F move is trivialized when you consider specific junctions formed by M, and dagger, and topological defects taken to be A. Okay, and let me make sure I answered Masahito's question. Sorry, did I answer your question? Or?
Well, let's see. Well, I still need to see. I mean, whether it's finite or not. But, yeah, I mean, the question was whether there are finitely many possibilities.
Ah, yeah. So I didn't say. So okay, good. Yeah. So because these are going to be polynomial equations in M. Okay. So F symbols are already fixed. They're going to be polynomial equations in M, there will be finite number of solutions. It's not totally obvious because there's a gauge freedom associated with junctions. But once you fix those gauge freedom, you can show there's only a finite number of solutions. Okay, that's not totally obvious. Okay.
Yeah, this data looks like.
But sorry, let me say it differently. But there's a different way to prove it's finite. It's using the relations between this kind of algebraically. It's using the relation between this algebra, the existence of the algebra objects, to the notion of a module category associated with the fusion category. And you can show that there's only a finite number of indecomposable module categories.
I see. Oh, sorry. How do you see the connection to the modular category? I mean,
module category.
Module category.
Yeah. So that will come later.
Oh, okay.
Yeah. But I don't. Yeah.
Yeah. If you view this one A and cycle as onions,
yeah,
the data described looks like it's condensed algebra. So
yeah,
that's a,
very good.
That's
so
higher dimensional understanding.
Yeah. So if you look at the condition, you see that I dropped one condition, which is the case, which is required when you want to talk about when you want to talk about condensable anion, which is commutativity. So I'm not requiring commutativity, okay? Which is what you require if you want to do condensation in the bulk.
I see. Okay. So the related but not identical. There's a.
This is more general.
This is more general.
This is more general.
Okay. Thank you.
Okay. All right. So how much time do I have?
9 minutes. But you
okay.
can take 5 extra minutes.
Okay.
Yes.
Yeah.
15 minutes then.
Yeah. Plan strategically.
And maybe related. Do you have an example that we have a gauging but not a closure of the condensed algebra?
Come again?
No, here we could have a gauging but beyond the condensed algebra. There's A which is not condensed algebra, but you can still be gauging. What is the example? Condensable algebra. You say your condition is weaker than condensed algebra.
Yeah, you can do higher gauging with this set of algebras already in 3-dimensional TKFT. This will give rise to surface operators. Okay. Yeah, higher gauging meaning you gauge it only on not on the 3-dimensional space where you need commutativity, but you gauge on the 2-dimensional subslice.
I see.
Yeah. All right. So once you have this machinery to do generalized gauging, there's one procedure you can already do known as half gauging. And this leads to topological interfaces. And this is something that related to what Clay talked about, I suppose, last week. And the picture is very simple. Is that suppose you have a theory T with symmetry described by a category C that contains some algebra object, A and M dagger, describing the morphisms. You can consider gauging, half gauging, namely inserting a network of these topological defects, for example, like this, in the theory T. Okay, that amounts to, with insertions of observable as operator equation, that amounts to putting an interface between the theory T and its gauge cousin. Okay, and this topological defect, so let me use the red color. This object A essentially gives rise to the so-called Dirichlet boundary condition, which you heard from Clay's lecture, for this half gauging process. And that's important to ensure that you get the topological interface. So let's denote topological interface by I. And furthermore, you can obtain the original algebra objects by fusion of the interface and its orientation reversal. Namely, you can put this picture and you put another copy of the same topological interface with this orientation reversal. It will be interfaced back to the original theory. And by fusion of this I and this orientation reversal, you'll be doing essentially gauging A in the strip. And in the limit where they are close, because they're topological, and there's no cost in doing that, you recover the original algebra object A. So here I want to say, but I did not have to explain in full detail, is that there's a correspondence between half gauging and topological interfaces, or generally families of topological interfaces. And in a special case where the special case where the theory is isomorphic to its gauged cousin. The corresponding interface gives a topological defect line in the original theory. Okay, and this is one way you can discover new non-invertible symmetries by playing with generalized gauging, and that has been studied in various papers. And just to give you, let's end with some one non-trivial example. Let's study the case of tricritical Ising. Okay. In this case, the theory has a very simple Lagrangian description. It has described by the phi cube scalar field theory, just like Ising is described by phi to the fourth theory. And as I said before, it has 6 primary operators, and there are fusion category symmetry described by the Ising category together with the Fibonacci category. In particular, the Fibonacci category acts on the local operators in a very simple way. Act on the, so this is the phi to the fourth theory, sorry, phi to the sixth theory. Act on the phi operator. Normal ordered by giving rise to this non-trivial eigenvalue. And this is the operator that becomes dimension 3 over 80, 3 over 80 at a fixed point. And you can ask, what are the symmetries that can be gauged in this theory? And you find so it refers to the symmetry that can be gauged are gaugeable algebra. So again, it amounts to saying what the object is and what the morphisms are. And you find the gaugeable algebras are of the following form. And 1 plus eta, which is the one that we already know, is coming from gauging the Z2 symmetry. But there's interesting another one that's coming from 1 plus W, where W is the Fibonacci, the generation of the Fibonacci symmetry. And you can ask, what happens when you gauge the symmetry? And what you'll find is that both of them leads to self-dualities. Okay? And the reason that gives to self-dualities is because in either case, they can be written as the square, the product of topological defects within the same theory. This case by the duality defect itself, in this case by the Fibonacci defect itself. And if you go back to this picture, this amounts to saying that there's a case where this algebra object you gauge can be factorized into actually topological defect, which are special case of interface between the same theory. Okay? And that explains, follows from the second line. It follows from the second line that the theory is actually self-dual under gauging this process. And this is something you can explicitly check. But the upshot here is that the tricritical Ising CFT is self-dual, not just under the conventional Z2 gauging, but also under gauging the Fibonacci symmetry. And let me just take a minute to get back to I think I have 2 minutes, right?
Yeah, 2 minutes, but 2 plus 5, so 7 minutes.
Okay. Yeah. So let me just take a minute to get back to Masahito's question, namely where the module categories comes in. It comes in the fact that its topological interfaces come with the family. So I'll not write words just to save some time. The topological interfaces come with families, and the families are generated by fusion of defect lines in the theory T with a given topological interface. And you can take the particular simple topological interfaces, and those are the objects in the module category. Okay, they have an action from the topological defects from the left. This will be a left module category over the fusion category generated by the topological defects. And the important information in the module category beyond these objects are morphisms that tells you how topological defect lines in the theory T can end on those interfaces. They give rise to, in general, interface changing operators. Okay. All right. Yes?
So, are there any kind of interesting flows which are protected by the Fibonacci symmetry?
Yeah, so there is one flow by turning on the sigma prime operator. one of the spin operators in the triangularizing CFT that preserve the Fibonacci symmetry. And that case flows to a gapped phase. I think with you can show that using the symmetry again, you can show that because the Fibonacci line has non-trivial quantum dimension, the phase, if it's gapped, has to be non-trivially gapped, and you find that at the minimum you have to have 2 ground states, and that has been confirmed by numerical analysis. That was confirmed by numerical analysis. Yeah.
But that one is not integrable.
It's not integrable. Yeah.
If you use W as a local operator, what are their scaling dimensions?
W as local operator.
You know, eta, is that scaling dimension 116, 116? The eta operator.
You are talking about the anyang. So if you think about it as anyang, the endpoint operator.
Yeah, that's right.
Yeah. No, eta will correspond to the energy operator with dimension 1/2. Yeah, 1/2, 1/2.
Then what about the W here?
W, I don't remember on top of my head. It will correspond to one of the energy operators. Yeah. Yeah.
That's some, you mentioned some,
yeah.
305, 305, something like
yeah, it could be 305. Yeah. Yeah. All right. Okay. So what's something more exciting? Let's talk about the RAP-DA symmetry that you have seen in the previous. Okay, I'm still getting. Okay. Let me just use this board. So the example I'm giving you are the simple examples. There are much more to be explored in terms of this examples to be explored that has the same flavor as above, namely self-duality under generalized gauging. But here is another example of a slightly different flavor. This example involves this RAP-DA symmetry that you have seen before in Shuheng's lecture, so I don't have to introduce it anymore, except to just to remind you that there's a single non-invertible topological defect in this game. It has quantum dimension 2, corresponds to the 2-dimensional representation, irreducible representation of D8, and has the fusion rule that squares to the 1-dimensional representations, which are labeled by eta and eta prime, as follows. Okay, so the product are given by the tensor product of the corresponding 1-dimensional representations, and the eta and eta prime they generate Z2 times Z2 subsymmetry category within the RAP-D8. And there's a classification that you can pursue to understand the gaugeable algebra in this theory, which I did not describe, based on the interface picture. And from that description, you find there are 12. There's a huge zoo of symmetry that can be gauged. There are 12 gaugeable algebras. Okay. So and in particular, there is the maximal gauging, which amounts to gauging the whole category, okay, of the form when the algebra object A, as an object in this symmetry category, is just the sum of these topological defects, the simple topological defects, multiplied by their corresponding quantum dimensions. One can show that the coefficients, once you fix this, the appearance of identity in this algebra to be 1, which is something you want to impose physically because you want to ensure that after gauging this object, you have a unique ground state. The other coefficients are bounded from above by the quantum dimension of the corresponding topological defects. So this is the maximal in that sense. And once you write down these algebra objects, you can go ahead and solve the rest of the consistency conditions to figure out what are the multiplication maps M and M dagger. And you find that there are 3 possibilities. There are 3 solutions. And I label them by 1, 2, and 3. And they correspond to the 3 SPTs that Shuheng talked about for RAP-D8. Okay, and they are analogs, as I said before, of the discrete torsions that you encounter in gauging group-like symmetries in the conventional orbit field. And you can ask, what happens in the physical theory with the symmetry under gauging this symmetry, under gauging this algebra. So one example is where the symmetry is realized is the symmetry is the orbifold branch of the C-equivalent boson, which we talked about in the first lecture. In the sense that this rep D8 is a symmetry subcategory of the orbifold branch. S equal to 1. And the symmetry category, the symmetries on the orbifold branch is actually extremely rich as far as non-invertible symmetries are concerned. Even though you lose the invertible continuous symmetry on the circular branch, many of the, all of them reincarnate into non-invertible symmetries on the orbifold branch. In particular, this rep D8 is part of this family. And you can ask, if you start from the orbifold theory, namely at the radius r, okay, the orbifold theory at the radius r, what happens when you gauge this maximal algebra? And what you find is that there are two possibilities. So the three possible gaugings actually leads to only two outcomes in this case. One of them leads to the theory on the circular branch. Okay, and the other two possibilities give rise to the theory on the orbifold branch, but at a different point at the radius 4 over r. Okay, and the reason that these two gaugings leads to the same consequence is because of the larger symmetry in the theory, which makes these two different algebras, different looking algebras, becoming equivalent. And then mathematically, they correspond to the fact that there are Morita equivalent algebra objects in the bigger fusion category, even though they are not Morita equivalent in this rep D8. Okay. And if you look at this relation, you also see that the special point when r equal to 2 is self-dual. Okay, under this process. And from the half-gauging process that the half-gauging procedure that we described above, this implies there's an even bigger symmetry at that point. And that point is the Ising squared point on the orbifold branch. And indeed, as discussed in a number of papers, including the paper I referred above, but also another paper. Let me find the reference. This is by Choi and et al., and also by including Xin Yang and the collaborators, where similar kind of self-duality under generalized gauging in this theory have been explored. Okay. Okay. So with that, let me end my lectures.